you'll notice that, real snakes don't have legs. And the reason why biology evolved or God created, whatever your view is, the snakes without legs is so the animal can get and burrow through these tight spaces without the legs getting caught on things. The other reason why, and this is something that we've observed in our group, is you only have so much muscle in your back. And if you dedicate some of that muscle to small legs, it's a waste of space. So it makes sense to put as much muscle as you can into your back if you're getting through a tight space. So in medical robotics, the challenge is getting as small as possible, but still retaining maneuverability and strength. The thing is, you only have to go so far with medical robotics. Distance travel isn't that great. So you can play some tricks in design in having a lot of your actuators, your motors, your computers off board. With Snake Robot for search and rescue, the robot has to go very far, about, say, 500 meters. And for that, you need to carry all of your motors, all of your computers, all of your sensors, and your power with you as you go. So that's a different set of challenges, and therefore it gives you a different type of design. I'm used to failure. Trust me, I'm no stranger to failure. It's disappointing when you think of an idea and you think everything's going to work well and it doesn't. But I firmly believe if you have the best of intentions and if your intentions are good and you're honest with what you're trying, and at the same time you're trying something new, as long as you keep learning, it's just inevitable that you're going to succeed.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwayne, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast.
Challenge into robotics so far. What do you think the main point still we can figure out in robotics?
I'm always asked, what is that one thing in robotics that we haven't quite figured out yet? And the answer is, there is no one thing. Robotics is multidisciplinary. There's so many things that go into robotics. I can list some, perception, action, manipulation, cognition, machine learning, interaction with your environment, human-computer interaction, just to name a few. There's so many unsolved problems in robotics.
Great. So when you look for snake robots, exactly, is it a choice? Why choose snake robots? For example, you have been working that for many years, but do you think there's maybe other inspiration to design robots that could be, navigate confined environment rather than a snake robots?
So the idea for a snake robot wasn't mine. It was actually Professor Hirose in Japan. Actually, in 1971, he built a snake robot. And then I got introduced to them from my advisor, Joel Burdick, and his student, Greg Chirikian. And now Greg is a department head at a university in Singapore. They built the first snake robot in the United States. And I went to grad school with the interest of navigation, figuring out where robots should go. And when I saw the snake robot, I thought that's an even more amazing robot to plan for because it has so many joints, so many degrees of freedom that you have to coordinate in order to produce purposeful motion. So the idea wasn't mine. The reason why we want to build snake robots is they support a lot of applications, and some of those applications include search and rescue, inspection of facilities, medicine, and so forth. And in all of these applications, one of the common denominators is getting into tight spaces, small spaces, where people and machinery otherwise can't access. So, for example, in surgery, you don't want to get surgery, but if you have to, you want to do minimally invasive surgery. The idea with minimally invasive surgery is that the incisions are smaller, so the patient doesn't experience anywhere as much pain. The problem is minimally invasive surgical tools so far are limited to laparoscopes. Those are rigid, and linear, so they can only go within a straight line from the point of incision. Or you have endoscopes, there we go. And those instruments can either go very shallow into the body, or they can navigate the luminal spaces, like your large intestines, for example. The surgical snake robot gets the benefit of both. It's both rigid and flexible, and therefore you can navigate the cavities in the body, like getting to the heart, for example, without breaking this bone. So that's just one example of where you can use a snake robot. I have to say that the snake robots we use for search and rescue are much, much more different, very different. They're different beasts than the ones we use for medicine, and the ones we would use for manufacturing are completely different from the ones for medicine. In the United States, we have this phrase that Eskimos have 28 words for snow, whereas to us, it's just snow. But if your life is snow and ice all day, you can see why there would be 28 variations. So it's just the same for me too. I think there's all different types of snake robots. Now, to answer your question, why build the snake as opposed to other shapes? The reason why the snake robot is so good is not only can it pass through tight spaces, small spaces that people and machinery otherwise can't access. Well, actually, that's the reason why they're so good. But you'll notice that, real snakes don't have legs. And the reason why biology evolved, or God created, whatever your view is, the snakes without legs, is so the animal can get and burrow through these tight spaces without the legs getting caught on things. The other reason why, and this is something that we've observed in our group, is you only have so much muscle in your back. And if you dedicate some of that muscle to small legs, it's a waste of space. So it makes sense to put as much muscle as you can into your back if you're getting through a tight space. So that's why I think snakes are interesting, as well as they produce some good applications.
That's interesting. Maybe I'll ask again about the question. You mentioned that snake design and manufacturing is different from medical one and maybe research and rescue. But can you highlight what's the difference? And also, when you design, should you exactly replicate what you saw already in a real snake? For example, we see some robots, if you do exactly the same motion, you can reach singularity, and then you have complicated problem and control, if you can correct me. But which level of abstraction you need to get here as design for each case?
So you asked two questions. One is about biological inspiration, and then what was the first question?
About, you mentioned that the snake design and manufacturing is different from the medical one.
All right, so let's do your first question first. So in medical robotics, the challenge is getting as small as possible, but still retaining maneuverability and strength. The thing is, you only have to go so far with medical robotics. Distance travel isn't that great. So you can play some tricks in design in having a lot of your actuators, your motors, your computers off board. With a snake robot for surgery, with a snake robot for search and rescue, the robot has to go very far, about say 500 meters. And for that, you need to carry all of your motors, all of your computers, all of your sensors, and your power with you as you go. So that's a different set of challenges, and therefore it gives you a different type of design. For manufacturing, the robot has to perhaps handle large reaction forces, either because it's carrying a heavy weight or because it's punching holes, applying fasteners, and so forth. So the requirements are just incredibly different among these different applications, and therefore the robots are different. So the other question is, what about biological inspiration? Yeah, so first, I don't believe there are true biologically inspired robots. So the truth is, we did see snakes, and we were inspired by the overall shape and design of the robot, or overall shape of the animal and how it moves. But it's not like we cut the animal open and looked at its bones and its muscles and its nerves. We can't do that. It's impossible. But in understanding the fundamentals of how these animals move, we were able to translate some of those fundamentals to the real robot and get the robot to move. But actually something more interesting, I think, happened. And that is, because we needed to make the robot move, we developed an understanding of biological snakes that the biologists didn't know. So it's sort of a two-way illumination. Yeah, we were inspired by the biology, but we also figured things out for the biologists. And in this cycle that we have, I've been working with a colleague at Georgia Tech named Dan Goldman. He's actually a physicist. And he's really good at looking at what our robots do and mapping it onto the fundamental physics, and he knows the biology very well. And we have this nice, he thinks he's telling us how the robots work. We think we're telling him how the systems work. But it really has produced a lot of insight into how to make robots and work better and understand the animals. So one example is in 2011, my group here at Carnegie Mellon, took our snake robots to Egypt to do some archaeology work. But the ancient Egyptians, what they did is they built these ships out of modular pieces, and then they would then carry the pieces from the Nile to the Red Sea, assemble the boats, and then sail. And then they got tired of ferrying the pieces back and forth, so they dug some caves and hid the modular ship pieces in these caves. And it's pretty remarkable, because these boats are 4,000 years old, and they figured out how to do modular design where any piece can go into any ship. And I might add, they did that without the benefit of tools. So they had notches and holes. It was pretty great. They also had a lot of rope. So I got to see 4,000-year-old rope, and it looks exactly like rope today, in these caves. And the wood, I should also point out, was from Lebanon. So they had something pretty extravagant going on back then. But now these caves are hard to access, and there are a few of them left because tomb raiders went through and took the wood and used it as firewood maybe. So we were there to send the robots into these caves, but we were challenged by the sand. In other words, we couldn't go up sandy slopes. And then after working with Dr. Goldman at Georgia Tech, him understanding some of our work, us understanding what he's teaching us, we were able to create motions for our snake robots based on what sidewinders are doing to actually go up sandy hills. We figured out how sidewinders worked. Dr. Goldman educated us that much more about sidewinders, and then we were able to make our robots to get the robots to overcome challenges that we couldn't in Hurghada when we were back in 2011.
I want to ask you here also about the hybrid design. You mentioned a really very interesting story about this robot, which I think very well known in 2000, early 2010, I think this time frame. But when you look for the design of the snake, for example, you mentioned the environment, like the sand. Sometimes this even the snake could not be functioning in certain environments. And that's why I'm asking you, do you try to use, I don't know, ever thought about using hybrid design, for example?
So first, there's the issue of snakes working in different environments. And another observation that Dr. Goldman helped us with was we realized that there are some snakes which we call specialists, and they only work in certain environments, and outside they're not going anywhere. And then there are generalists who can adapt as they go, and those guys. There's no reason to think a generalist can outperform or underperform a specialist in the specialist environment. That's just how it worked out. But in terms of a hybrid design, the robot is generally homogeneous. The reason why it's modular. And if you can build the same module over and over again, you have the ability to, build lots of snake robots and repair lots of snake robots in the field. But we are developing other modular structures now. So instead of just building snakes, we are building wheeled robots, legged robots, all sorts of robots out of the same modules that evolved from the snake.
Great. I'm curious to ask you in that case, when you look to the modular design for robots we have, it's more compliant, but when you look to the field now, we have soft robotics, we have the rigid one, and you try to more the modular design to be more compliant. Do you have any disagreement or criticism, like for example, in certain way of design, you think, well, maybe this is not the right way to invest time and resources on this design?
So there's been a lot of energy put into the design of soft robots, and I don't know if the soft robots found their application. Maybe for grabbing objects, soft robots are good, but certainly people would say you need soft robots for surgery. And I would hardly characterize the surgical snake robot we developed as a soft robot. And yet we've operated on 1,500 people and no soft robot has. I think you really have to let the requirements drive the decision as to what you want. So our robots generally, in some ways, they are hybrid. In other words, they're hard with some soft interior to allow for compliance, but they're not exclusively hard, nor are they exclusively rigid. Soft nor exclusively hard. It's somewhere in the middle.
And since you mentioned at the beginning that we have the sensor actuator maybe inboard or maybe external, when you look to physical intelligence, how you reduce the sensing and more depending on intelligence maybe in the design to be embedded in the structure?
I think in physical intelligence is a big deal. A lot of us think that our brains are the most intelligent part of our bodies. And maybe that's true. Maybe that's how we're distinguished from other non-human animals. But there's intelligence in our hands, in our arms, in our legs. It's our designs are optimized to move around, optimized to perform tasks. We're optimized to use our hands to build things, and our vision helps us, understand how to build things and how to avoid trouble. So I really believe that let's use biology, for example. The wing of a fly, which may seem simple, there's tons of sensors on that fly, on that wing of that fly. And it's feeling air pressure, it's feeling temperature changes, it's doing a lot just so that little system with only 386 neurons, 200 of which are dedicated to vision, can flap its wings and stay alive. It's pretty amazing. I don't think we've done enough in investigating physical intelligence in systems yet.
Mm-hmm. That's interesting. Can you maybe share a moment was surprising to you in during your career in research for snake robots, or maybe something maybe surprising? Sometimes you have a moment like, well, I didn't get that will happen in the design or whatever.
There were two. So one of them, this will sound very egotistical, but the surgical snake robot, I never thought I'd figure out how to make it. And one day I said, I'm going to figure this out now. And then 15 minutes later, I actually figured it out, which never happens. You always figure things out when you're not expecting it to. The other is my colleague, Matt Travers, he developed nice compliant controllers for snake robots going through piles of rocks, and he did it really quickly. I was pretty amazed. I'm also impressed with my underwater snake robots as well. We built that one pretty quickly.
I
So
want to ask you about the failure. If there is failure happening, especially snake robot, for how you deal with that failure, and do you think how you think also about redundancy in design here?
yeah, so one of the selling points people say about snake robots is that, you know, if one motor breaks, it's easy to keep going. And, there is some truth to that. Certainly, when I sent my snake robots into the pipes, the sewer pipes by my house, a couple of the motors broke and we were able to proceed just slower. And that's nice. But we really didn't design the controller, the behavior to adapt to the broken robots. We were just lucky that they just kept on working. But I think that kind of analysis is important to have.
Mm-hmm. Great. Maybe a few questions left. I want to ask you, what are other things you wish you can do for snake robots? I mean, or maybe other ideas you still aspire to achieve.
Oh, we cannot navigate unstructured terrain. If there's a collapsed building, you know, we're not ready to go through every possible point in a collapsed building, climbing around pipes inside or outside pipes. We still can't do that either. And finally, just dealing with different terrains over and over. There's a lot of mechanism, sensors, and algorithms that still have to be developed, and we haven't developed them yet. Yeah, I think the biggest problem we have is we don't have enough resources to do research. I know in the United States it may be more than other countries, but even here I still feel like there isn't enough. So that's probably one of our biggest problems.
So, can you share something like advice for a student maybe interested in the field of robotics, where you should start with?
Yeah, so if you're interested in robotics and you're getting into it, the good news is there's lots of videos online, there's even some online courses. But the thing I really stress is to tinker, is to try. Learn how to program and then write programs. Learn how to build things and then build them. Get your hands, the phrase we like to say in America is get your hands dirty. But robotics is not a passive sport, it's active. So please, learn how to build things, learn how to program. And then the final thing is make sure you're really good at math. Those are all important. And if you can master those three, learn how to, talk to different types of people. Because again, robotics is a multidisciplinary field.
Amazing. Maybe I want to ask you a quick question since you have expertise both in academia and a starting company. What's really different? I mean, what really changed in the perspective of the design when you try to do something from in the lab and something for a company? What is different?
Yeah, so with the company, you have to make something under a certain amount of time that someone's going to want to buy. Someone has to want it, and you have to build it quick enough. In academia, you just have to discover a new truth, and your time horizon is a lot longer.
And is it a good thing or bad thing? I'm just curious.
They're different. You can say in the company, since time is short, how often can you innovate? Because you're just surviving to sell something to your to your customers. But on the flip side, in academia, if you have all the time, sometimes if you don't have a sense of urgency or even grounded in reality, you can go off and just think about things that may not be useful or even may not be interesting. So it really, it goes both ways. Likewise, in academia, ultimately all the breakthroughs that we're seeing in artificial intelligence and robotics, they all came from academia. because the smart people had the time to be creative. But not most of what comes out of academia doesn't become commercial product.
Mm-hmm. And do you think, maybe quickly, do you think when you develop something new, in which basis do you think it would be successful? When you have Snake Robot, I remember one of your talk, you didn't think you should start a company, and someone told you you should do that. But in which basis you know that will be successful or not? Do you have a criteria for that?
No, you have to go with your gut feeling, but then afterwards, you have to raise money. And in order to raise money, you have to convince investors there's a market. So then you have to go do research to understand what existing markets are there, what needs are in those existing markets, or maybe create a whole new market. And again, try and express to investors what the possible upside is. And if you convince them of all that, they'll invest in your company. You give them ownership of the company, obviously, but that's a hard thing to do, and it takes a lot of creativity and a lot of hard work, just like anything else.
Yeah, yeah.
I want to ask you this: you have like hard moments in research, or maybe like a failure or something.
I'm used to failure. Trust me, I'm no stranger to failure. You know, it's disappointing when you think of an idea and you think everything's going to work well and it doesn't. But I firmly believe if you have the best of intentions and if your intentions are good and you're honest with what you're trying, and at the same time you're trying something new, as long as you keep learning, it's just inevitable that you're going to succeed. I have proposals rejected all the time, but the ones that are good, that I think are good ideas, I get the reviewer feedback and I iterate on the feedback and I keep pressing, and then it's just a matter of time and energy for that idea to get funded. But you need persistence.
Mm-hmm.
Do you have moment of fear that you have? I know you have established already maybe in Snake Robots, but do you have moment of fear if you have different idea how would be accepted, maybe from academia or industry, both?
No, and I've never was scared by a new idea or failure in research. I just recognize research as a process, and what you try and don't make work is just part of the process. But it's not to say you try things at random. Everything that I've tried that didn't work out, again, eventually is adjusted, altered, and then with, again, hard work, effort, and again, some ingenuity, eventually becomes good.
Yeah, yeah. So the last question for you: what makes you fulfilled?
I don't know. Of course, I'm proud of my kids. They're good little boys. That's good.
Yeah.
I guess one thing I really find fulfilling is when a student starts figuring things out that I couldn't figure out. I like that a lot. When a student proves me wrong, that's pretty great. If I figure something out because of the student, that's always nice. And then afterwards, really great robot demonstrations. That's what I find most fulfilling.
Interesting. That's great. Yeah. Do you have any advice you can share? Maybe if you have any advice or given to you, and you think it's very important.
It may sound trite. It may sound trite, but pretty much the best advice is, people when they work on something or want to do something, they have to be honest, with themselves. And I think a lot of times people have a hard time I think we all do, knowing exactly what they want and then pursuing it. I always admire people who know what they want and then know how to go after it.
Mm.
So I guess that's the first. And then the other is, don't be afraid to leave your comfort zone every so often. That's where you find new things.
Yeah.
I just don't, maybe one example of why I left my comfort zone was when I was a grad student. I worked in Japan for a summer.
Yeah.
Certainly going to Egypt, I never felt like I was scared or anything like that. But leaving your comfort zone every so often is a good thing to do.
That's really good advice.
Yeah.
Yeah, be honest and then leave your comfort zone.